Bismillah ar-Rahman ar-Rahim, my dear students of third year. The course is Biopharmaceutics and Pharmacokinetics, Ajman University. Now we will do part 3 of one compartment IV bolus administration. We will continue with what we left in last part. And before we start, we are going to just remind you of the equations that we discussed in last part. Okay, first, you remember that we said CP is equal to CP 0 phi e to the power of minus KL phi t. Also, we wrote it as ln is CP is equal to ln is CP 0 minus KL phi t. Also, we talked about delta CP divided by delta T is equal to minus KL phi CP. Okay, just looking at this equation, I need to explain it even further now. When we say delta CP means the change in concentration, delta T is the change in time. For example, let's say time 1 hour and then time 0. So I'm talking about here what happened in the change of concentration during 1 hour. Delta CP is, what is delta CP? Delta CP is the concentration at 1 hour. For example, let's say it's 80, for example, minus the concentration at 0 hour, let's say it was 100. Okay, this will be equal to KEL. طبعا negative here is just to indicate that this change is negative. شوفوا 80 minus 100 is negative. That's why we added this one. KL is the window through which the drug gets eliminated. And what about this CP? Is it 100 or sorry, is it 100 or is it 80? Now CP that we use here is the concentration at midpoint time. يعني we need to find the concentration at half an hour. Okay, and the CP that is here, we call it, what do we call it? The concentration remaining to take place in the elimination. Okay, يعني how much is remaining in the body. Okay, now we are going to talk about a new thing that is very important, which is the area under curve. طبعا, when we say area under curve, we are talking about the area here under concentration time curve. Area under concentration time curve. This is the area we are talking about. Okay, now this area is very important in different aspects. One, if you remember the definition of bioavailability, it's شو حكينا على bioavailability? It's the rate and extent of drug reaching the site of action. صح ولا لا? Rate and extent. What describes the extent? شو اللي بيعبر عن الextent? Of course, it's the dose that I'm giving, but maybe not the whole dose is getting inside the systemic circulation. So in order for us to know how much getting inside, we need to know about AUC, area under curve. إذن area under curve talks about إيش? Extent. Extent يعني the quantity that gets inside the systemic circulation. So if I have a product or two products of a drug, like for example a drug that is paracetamol, and I have two products of paracetamol, مثلا Adol and Panadol, and I want to compare these products من ناحية الextent. So how do I compare them? By comparing the AUC. The one with higher AUC will ايش معناته الextent is higher. Okay, if they are similar, then they are similarly absorbed and getting to the systemic circulation. إذا ال AUC رقم واحد تعبير عن الextent, and we use it to compare the bioavailability of products. And this is something important, and you took it in biopharmaceutics and pharmacokinetics 1. You took how do we compare bioavailability. The second importance of AUC is that it can allow us to calculate the clearance of drug. Clearance. And this is very important thing, similar to KEL. Okay, now this clearance is very important because clearance is used to design the dosage regimen. لما نسوي designing للدosage regimen, we need to know what is clearance, the clearance of the drug in the patient. Okay, going back, إذا حكينا شغلتين. We said two things. We said that AUC can be used to compare the extent of drug reaching the site of action or reaching the systemic circulation is better. Second, it can be used to calculate drug clearance in the patient. Okay, now, so how do we calculate AUC? What is the unit of AUC? Actually, if you look here, if you have, for example, a square, how do you calculate its area? You multiply, okay, one side by another, okay, and this is how you get this area. For example, A into B. Now, it is very similar here, except that the concentration keeps changing. It's not like we have a constant concentration and allowing us to multiply this side by this side. No, we don't have that. Actually, the concentration keeps changing. That's why you need to see these changes and take it into account. And these changes in concentration happens every second. That's why it can be described by a differential equation. Do you remember differential equation? Differential equation talks about changes, minute changes, التغيرات الصغيرة, the small changes that happens. Okay, that's why AUC is actually concentration في time. هي concentration في time, but you have to take into account the changes that happens in the concentration while time is moving. Okay, so we can write it as AUC is the integration of all these very small segments. يعني بدك أتخيل هون إيش every second I am measuring إيش the area. Every second I'm measuring the area until all areas are covered. And this is how we can do it. So we need to add together the changes in concentration multiplied في التايم. يعني what is the concentration that changes every second and multiplied by ايش the time, the width بنحكي له العرض, height by width. شوفوا, this is AUC for a very narrow segment, so you have to add them all together. طب I can do that by integration, and integration will give us ايش the following equation. And this is what you need ish to know and understand. So if I want to look at the changes that happens with concentration and multiply it by time, I can use the following equation, okay, to describe the whole process So if you see what is AUC, AUC is equal to dose, and remember here our assumption is 1. We are giving IV bolus. Second assumption, it's 1 compartment. Third assumption, issue with third assumption, first order. Okay, so this is what we have. Now dose divided by V, we already took it before as equaling CP0. يعني the dose that I inject at time 0 will give me CP0, right? طب how do I get CP0? It's the dose divided by the apparent volume of distribution. Okay? KL is the elimination rate constant. طيب, so it can be equal to CP0 اللي هو dose على V. CP0 divided by KL. طيب, later you will know that also, and this is very important, V of KL is equal to the clearance. And that's why I told you AUC can be used to calculate clearance. So I can write this one as AUC equals to dose divided by the clearance. طيب, you also will find out that for any route of administration, not only IV, and for any number of compartments, you can use the following equation to calculate AUC. If you know the clearance, okay, and you know your dose, and you know F أخذتوها, you took it in biopharmaceutics pharmacokinetics 1, and it's the bioavailable fraction. مثلا for example 0.9. 0.9 meaning قديش 0.9؟ 0.9 means 0.9 معناتها 90%. معناتها 90% of the dose gets to the systemic circulation. So if I know F with dose with clearance, I can calculate AUC. Anyway, I want you so far to focus on this equation. إنه assuming IV bolus, assuming 1 compartment, first order kinetic, then AUC can be calculated as dose a clearance or CP0 divided by KL. طيب, sometimes we don't know what? We don't know, let's say, the dose, or we don't know the apparent volume. In this case, we can use very famous approach called trapezoidal rule. Trapezoidal rule. Now, trapezoidal rule is a numerical way to divide the area under curve to segments. Yani, for example, if you look here, okay, let's say this is your, for example, CP0, and this is CP at 1 hour, and then CP at 2 hours, 3 hours, and so on, 4 hours. Okay, so we are dividing it to segments, and we are calculating the area of each segment. We are assuming that this area or this shape is trapezoid. Trapezoid يعني means when you have two parallel lines and two lines that are not parallel to each other. نحكي له بالعربي شبه المنحرف. شبه المنحرف. Okay, it's like a semi-disfigured shape because it's disfigured from this side. Okay. طيب, when we have this shape, we call it trapezoid. That's why it's referred to as trapezoidal rule. طيب, how can we calculate the area here? we can calculate it by multiplying this into the height. صح؟ طيب, there is a problem now. Which height? I have this height and I have this height. So which one will give me this area? طبعا, don't forget that this is the concentration height and this is the time width or the time interval. Okay, you cannot use the smaller CP, because if you use it, then the area you will calculate will be less. يعني this is ايش being omitted, يعني كأنه احنا بنشيل هذا. We are removing this. So the area you will calculate is less than the actual area. And if you use this one, then the area you calculate having this as extra. يعني you are calculating larger area. So instead, what we do is we use average concentration. يعني this CP plus this CP divided by 2, and we will get it somewhere here. Okay, so this is the concentration that we are going to use as CP. إذن تخيلوا معي التالي. This is, let's say, T1 and this is T2. This is CP1 and this is, sorry, not this one. This one CP2. Then what do? You say, okay, I'm going to multiply this width اللي هو T2 minus T1 multiplied في الهايت. الهايت هو average of these two. So it's CP1 plus CP2 divided by 2. This is how we calculate the area of the trapezoid. Now it's very important that the time interval is as short as possible. لازم يكون ايش؟ short. For example, I cannot take this point with this point واحكي خليني ايش؟ Let me reduce the efforts. So I'm gonna use these 2 points beginning and at 10 hours and let me find the area. No, that's wrong. بصير عندكم errors very high. Why the errors will be very high? Because remember that here it's a curve. يعني here, okay, if I draw again the trapezoid. Okay, it's actually a curve. But in trapezoid we are assuming that it is ايش؟ A straight line. فبالتالي there is some error. In order to keep this error as less as possible, we need to have ايش؟ shorter segments or a smaller time interval. So the smaller the time interval ايش؟ the more accurate is your AUC. Even though this is an approximate way, اللي هو trapezoidal rule, it's more frequently used because you do not need to assume one compartment or you do not need to assume first order kinetic, etc. You do not need to assume that. Okay, that's why it's used more frequently. But let's go again and try to understand how we can do the calculation. طبعا this is one of the segments. يعني what you see in this equation is one segment only. In order to know the whole area, you need to add all the segments together. شوفوا here we are multiplying the width اللي هو time interval into ايش؟ the average concentration. Look at this figure. Okay, you will see this segment, for example, CP2 يعني at 2 hours, CP3 at 3 hours, and this is 2 hours and 3 hours. So we multiply the difference on اللي هو 1 hour multiplied by the average. Average يعني it will be this concentration. Okay, this concentration 45 probably. Okay, now what do we need to do? We need to do this for all others as well. For this segment for this segment. We need to know what is our CP0 to calculate this one. We need to know also, we need to calculate the area of this one, the area of this one. What is the problem? The problem is we don't know what's happening here. Theoretically, it takes infinity time to approach the zero, to reach zero. تتذكروا الفراكشن remaining e to the power of minus KEL في t. We said it's from 0 to 1, right? It's 1 متى? When the time here is 0. طب 0 actually it will never reach 0. يعني put e to the power of very large number minus billions here and it will not give you exactly 0. Okay? That's why theoretically the fraction remaining قديش? The fraction remaining will never reach exactly 0. So how can we calculate this area? There is a way by integration. There is a way to do that. Now I want you to consider two situations. One, if you have the assumption that you have one compartment, okay, first order, هذا assumption, okay, وعندكم two, you have assumption first order because that's true for many drugs, but you don't know how many compartments you have. Okay. طيب, in the first case اللي هي if you know that you are dealing with one compartment and first order, then in this case the last area which is here, this last area will be equal to CP last. شو يعني CP last? آخر concentration I took it. طبعا these concentrations I take them from plasma. So last concentration and then divided by KL. And this will give me the area from this point till infinity. شوفوا, actually this is same as saying CP0 على KL. شو CP0 على KL? شوفوا, CP0 على KL will give me the area from here to infinity. اللي هي the same equation we talked about before. CP0 على KL. هذا we assumed ايش? one compartment. طيب و CP last على KL راح يعطيني من this point and forward. Okay. طيب, how do I get KL? KL you can get it in this case by putting it in let's say similograph paper or changing the concentration to linear concentration, and then you get the slope of the best fitting straight line, and that from that slope you can get KL. طيب, if you do not assume one compartment, in this case put the data point in similograph paper. نيجي على similograph paper, put the points similograph paper, and then look at the terminal data points like last 3 or last 4 or last 5 that can actually make straight line. يعني ما تطلع على, you don't need to look at the first data points unless all of them look like a straight line. So look at the terminal data points, get the slope. The slope will be equal to minus K. هلا minus K هون do not refer to KEL because we don't know if we have one compartment or not. Okay, so we'll just use K. In this case, your last area will be CP last divided by K. You got it? طيب, to make it simpler, we will use the first assumption for now. And we know it's one compartment and we know that it's first order. That's why we calculated KL from the whole data points. لأنه إذا عندنا one compartment to first order و IV injection, all of them simulograph paper will make a straight line, and from that we can calculate the KL. Okay, let's now do some exercise. شوفوا. Previously I told you ايش? I told you that usually when you have data points and concentration more than 2, usually you need to draw a graph. In this case, maybe you do not need to draw a graph, depending on whether you are given KL value or not. Okay, but anyway, I want you to imagine the following. You have time with concentration. At 0 time, the concentration was 100. At 1 hour, 71, 250, etc. And these are the unit. Okay. Now you need to use trapezoidal rule. Okay, trapezoidal rule اللي هو as I already described. تخيلوا, imagine that you have time بالhour والconcentration أو CP خلينا نحكي بالمicrogram per ml. Okay, and imagine it's something like that. وهنا here we have 100. Okay, I'm just drawing for you to imagine the situation. Okay, so at 1 hour it's 71, at 2 hours it's 50, etc. So how do you calculate the first trapezoid? The first trapezoid بيكون الCP فيه at 0 hour 100, at 1 hour قديش؟ 71. طيب, والتايم انترفال هنا 1 hour وهنا ايش؟ 0 hour. فإذا you have 1 hour time interval, هي الويدث multiplied by the height. طب شو الهايت؟ الهايت راح يكون ايش؟ 100 plus 71 divided by 2, and that is equal to ايش؟ to 85.5. هذا هو الميد concentration. concentration جاي بالنص between 71 and 100. So multiply this into 100 will give you the area under curve for the first segment. وبنحكي لها delta AUC. This is that AUC, delta AUC. Okay. Something that I left and I did not tell you about is the units. I told you the units are very, very important. Okay, here what will be the units? You are multiplying time by concentration. So what the concentration here, for example, microgram per ml or milligram per liter, microgram per ml, and then you are multiplying that into hour. So this is your unit. Okay, so your unit is microgram, or you can write it as milligram per liter and then multiply it per hour. It is similar to this one. شوفوا, it's microgram per ml and then multiplied into hour. طيب, so the first area, which is this one, has an area of 85.5 microgram per ml multiplied with hour. Hiya. This is the first area. طب the second one, can you do it yourself or we'll do it together? طيب, شوفوا, the time here is 2 hours. We'll do it together. And the concentration here is 71, and here additional concentration 50. طيب, شوفوا هون الويدث قديش؟ width 2 minus 1 يعني 1. طب والaverage concentration, the middle point قديش؟ 50 plus 71 divided by 2 يعني 121 divided by 2 will give me 60.5. فإذا 60 0.5 اللي هو middle CP multiplied في الويدث اللي هو 1 and it will give me 60.5. فإذا here I calculated the area. طيب you can do this for the others but let us go just before the last one. اللي هي الاريا هون. For example look at the last two. At 8 hours هذا at 8 hours the concentration is 6.2 and at 10 hours the concentration is 3.1. Okay, can you do this? Okay, look at the width. الويدث عندنا 10 minus 8 يعني 2. وشو الافريج concentration of 6.2 and plus 3.1. شوفوا this is 9.3. 9.3 divided by 2. خلينا نشوف. Let's see. هاي 6.2 plus, I'm trying to get the average concentration, plus 3.1 equal, and then divide this by 2 will give you 4.65. فإذا 4.65 and then multiply it by 2. انتوا already قسمتوا هاي على 2, you already divide this by 2, now you are multiplying it by 2, so you will get the same number 9.3 ايش شو unit microgram per ml into hour. Okay, طيب this is what we get. طيب now what about the area here? Now what you need to do, because we know that this is one compartment, okay, IV bolus administration, we need to put it in a simulograph paper and find out what is the KEL. If we don't know if it is one compartment, what do? We put all the data points and look at the terminal data points and see if they make a straight line, and then we draw the best fitting straight line. Anyway, if you find your KL by doing that, or if it is given to you, then how do you calculate this last area after 10 hours? Because theoretically the concentration will never reach 0. Okay, so how do you do that? Take the last concentration low 3.1 and divide it, هذا بنسميه ايش؟ CP last. Then divide this one by KL. KL, where do you get it? It's either given or you need to put it in a simulograph paper and find out from the slope. So you write here the value of KL, and this will give you the last area. Type. After that, what do? You total all these numbers. Okay, if you total all these numbers, you will arrive at the area under curve, the total area under curve. طب شو هذا الرقم هون؟ It's the area under curve for the first and second segment together. طب والرقم هون, this number, with the third one, يعني the area under curve from the beginning till the third segment, and so on. I hope this is clear to you. Okay, now we are going to talk about a new concept. We referred to it before, and that is the half-life of the drug, or we call it sometimes biological half-life or elimination half-life. And it's the symbol we use is ايش? Let me just correct this one. Okay, so it's T half. Okay, T half, elimination half-life. To define it, it is the time. دائما نبدأ of time because this is a time, half-life time. Okay, it's the time for drug concentration to fall half its initial or starting concentration. Now we're going to show you how do you calculate t half. What is the equation do you use? The second thing, we will show you how to determine it using graph paper. Okay, is the equation one. What is the equation of half-life? Number two, how to determine this in a graph paper. طيب, in order for us to derive half-life, it is not required from you to derive it, but actually you should understand it. Okay, we can do that by different ways. One way, طبعا, you have already here maybe another way, but they are very similar, is to say Cp equal to Cp0 of E os minus KL في T. Okay, this is the starting equation. Now T half, بدي اخليها T half. متى بتكون T half? The time here is the half-life. When this concentration is half this concentration. معناته I can write this equation as Cp0 على 2 is equal to Cp0 في E os minus KL في T half. Okay, if you take Cp0 to this side, بصير عندنا ايش؟ goes Cp0 with Cp0, بصير عندنا half or 0.5 equal to E os minus KL في T half. طيب, don't forget هذا fraction remaining. Fraction remaining is half, 50%. This is very important. The fraction remaining is 50% or half. Half of what? Half of the original concentration. طيب, if you take ln both sides, بصير عندكم minus, let me erase this one. بصير عندكم minus 0.693 equal to minus KL في T half. So of course minus goes with minus, بصير T half equals to 0.693 divided by KL. Isn't there is an inverse relationship between half-life and KL. The larger the KL, the shorter is the half-life time of the drug. Okay, so this is the equation that you should be used when you want to calculate the half-life of the drug. This here we are assuming that we have first order kinetics and one compartment model. Okay, وطبعا I don't want you to forget that one compartment model is the most frequently used model in pharmacokinetics or in compartment models. Here one compartment. طيب, the second way to calculate half-life is to go look at the graph. Let's say we are putting the data points as you see it here, and then we are drawing the best fitting straight line. This is the best fitting straight line. Take any concentration. Initially, take any concentration. For example, in this case, شوفوا الconcentration هنا 10, 20, 30, 40, 50, 60. إذن هون he used 60, any concentration. انتبهوا, he goes to the line and he does not go to the points, because once you draw the best fitting straight line, then you have to use that line and forget about the data points. طيب, this is 60. What is half the 60? Is 30, صح? إذن we want to see the time for the concentration to fall from 60 to 30. شوفوا how do we do it? It's 60 at this time and it's 30 at this time. So what is the time it takes to fall from 60 to 30? You calculate that one. تحكوا T2 minus T1. Then we can do it by graphical way, using the graph to do that, simulograph paper with the straight line. We can do that. Now look at the relationships here. You have initially you have let's say CP0, okay, اللي هي highest concentration. After one half-life, this concentration will be ايش؟ half the initial concentration, يعني CP by 2. So 50% lost and 50% remaining. اتذكروا هاي 50% ايش هي؟ E to the power of minus KL في T. Okay? طيب. Now after another half-life, okay, 25%, شوفوا انتبهوا هون. 25% remaining, 75% lost. After 3 half-lives, 12.5% remaining, 87.5% lost. شوفوا, it's like this, 100 to 50, right? طيب now you are 50. شو الهاف؟ طبعا هنا 1 half life, 1 T half. طيب 50 now it will go to ايش؟ to 25. هذا remaining. هي صار كمان another 1 half life, صاروا 2 half lives. طيب 25 اللي هو هون راح يصير 12 and half. فanother 1 half life, صاروا 3 half lives. So this is what you are looking at. If you go to 7 half lives, شوفوا قديش will be lost. 99.219. Actually you will never reach exactly 100, and the remaining will never be exactly 0. This is the property of first order kinetic. هي صفة ال first order kinetic, is that you never reach exactly 0 theoretically. Okay. Now in general, and this is for many textbooks, they say practically يعني for practical purposes, we consider the drug to be eliminated after the passing of 5 half-lives. 5 half-lives يعني more than 96% of the drug is lost and the remaining is less than 5%, يعني 3.125%. This is يعني this is correct for so many textbooks. Some textbooks say no, we will consider the drug to be eliminated after 7 half-lives because more than 99% of the drug will be lost. But for you have 2 assignments from your textbook. You can see the answers there as well. Let us solve them together. The first question, it says, how many half-lives would it take for 99.9% of any concentration to decompose? Assume first order kinetic. Here I want you to imagine the following. You gave a drug injection, an injection of a drug, an IV push we call it, and then 99.9% of that push is eliminated. Okay, now the remaining is راح يكون ايش؟ 100% minus 99.9%, and this will give you 0.1%. 0.1% يعني equal to 0.001. Okay, this is what it's equal to. Okay, so it's like I'm saying that the remaining in the body is 0.001. Now which equation or which mathematical term will give you the fraction remaining? Is on 0.001 is the fraction remaining. You remember when we talked about E, let me write it for you, E to the power of minus KL في T is the fraction remaining. تتذكروا؟ So the fraction remaining E to the power of minus KL في T is equal to 0.001. طيب he wants to know how many half-lives. قديش راح يمر من half-lives exactly so that most of the drag is eliminated and the remaining is 0.001. So we use this equation. If you take ln both sides, بصير عندنا from this side we have minus KL في T, and from this side let me calculate that what is ln 0.001 ln, so it's minus 6.908 908. Okay, so what is the time? Minus goes with minus, so time will be equal to 6.908 divided by KEL. But what is the relationship between this and half-life? You know that the half-life is equal to, for any drag, it's equal to 0.693. طبعا لما احكي for any drag, I mean that follows one compartment model, first order kinetic. It's equal to 0.693 divided by KL. هاي هي half-life. So what is the relation between this and this? This is the time taken for 99.9% of the drag to be eliminated. And this is the time for 50%. So how many half-life? We divide اللي هو 0.69 we divide 6.908 divided by KL, and then divide that by half-life اللي هو ايش half-life 0.693 divided by KL. طبعا KL goes with KL, and what we will have is simply 6.908 divided by 0.693. So here I will do that. This is the number and divided by 0.693. شوفوا, it tells you that you need 9.97 half-life. 9.97 half-life. Almost 10 half-lives you need. Almost 10 half-lives you need for the drag to be eliminated or decomposed 99.9%. Is that clear? Let's talk about the second question here. If the half-life for a decomposition of a drag is 12 hours, إذا أعطانا هون half-life T half, how long will it take for 125 milligram of drag to decompose by 30%? Assume first order kinetic. طيب, let's talk about how to solve this. عندنا هون it says 30% decomposition. 30% decomposition. معناته how much is remaining is 70%, صح? Where did it go? Okay, let's go back here. Okay, so we have 70%. 70% يعني قديش? How much 70%? يعني 0.7. The fraction is keeps changing. Okay, the fraction is 0.7. This is the remaining. So 0.7 equal to e to the power of minus KEL في T. Okay, again let's take the ln of both sides. So this will be equal to minus KL في T and 0.7 0.7 ln is equal to minus قديش 0.357 okay, minus 0.357. طبعا negative goes with negative, and then you will have T equals to 0.357 divided by KL. طيب, now so what is the time? Now you have two choices. عندكم two choices. First, you can calculate KL from this half-life, لأنه إحنا بنعرف إنه إيش الهاف لايف is equal to 0.693 على KL، فبالتالي I can get KL. بحط KL هون وهنا half life اللي هي ال 12 and then I do the calculation. The other way is just I divide this number by this number. بحكي لي كم half life and then I multiply it by 12. So I can choose any one of these methods. So I can divide this number by 0.693 equals, and then multiply it into 12, and you will see that we need 6. The time that we need is 6.176 hours, okay, in order for 30% to decompose. شوفوا 30% is not 50%. If I say 50%, I need 12 hours, but for 30%, I need a dish 6.17 or 18 hour. As I told you, the other way is to calculate KL. KL will be equal to 0.693 divided by 12 hours. So this is the other way. 0.693 divided by 12 hours equals, okay, so you have KL equaling 0.05775. 05775. okay, طبعا اليونت don't forget it as hour to the power of -1 لأنه الهاف لايف بالhour. طيب, now use it here. Okay, we'll use it here. 0.34 or high 557 divided by 0.05775. okay, and you will get برضو similar number or the same number, 6.18 hours. Okay, so these are the two ways to complete or to solve the question. Now we're gonna talk about a new thing, and we're going to imagine what happens to the drag. Okay, before we start, I'm gonna draw something for you. Before one compartment, IV Bolus open model. طبعا open في عنا here we have a window and through which the drag leaves, and the size of the window we will call it KEL. okay, this is the size of the window. طيب, now I want to take this window and make it bigger so that you can look at it. إذا أخذت الويندو اللي through which the drag leaves the compartment and I put it here. طيب, you know the drug, how does it get eliminated? It's not one process. Usually it consists of metabolism and excretion, right? So this window is actually, we can consider it as a sum of two windows. Okay, وعبارة عن two windows together. Okay, one that is for excretion مثلا. طبعا the size of the window is different for different drugs. One for excretion, also the size of the window for excretion also different for different drugs. For excretion I will call it ايش KE. KE يعني excretion rate of elimination or rate of excretion constant. نسميه rate of excretion constant. There is a window for metabolism. Okay, يعني the drug is removed by two ways. In this case we have the metabolism and the excretion. So the dose that I give eventually will leave through this big window. Now Km in this case, شو مال Km? I gave it a smaller size compared to Ke. Okay, it's just an example. Now some other drugs will have Km larger than Ke, and so on. Now the concept that I will be talking to you about, what happens, طبعا when I say Ke, I'm talking about excretion, which is normally happening where? في الكدنيز, صح ولا لا? It happens in the kidney. What happens if this gets blocked? شو يعني? يعني you have kidney failure, for example. The patient has kidney failure. But the only way for the drug to be removed is through metabolism. So initially KL is equal to Km, is an KL اللي هو the whole window is equal to Km plus Ke. If Ke is fully blocked, or let's say we have failure, we may only end up with Km. Km already small مقارنة في الKe أو في الKL, already small. So this will result in the accumulation of the drug inside the body. It's not leaving the body easily. So if I keep giving the same dose at the same frequency, what will happen? The concentration of the drug in the system will be toxic. So I have to reduce, of course, the dose and the frequency of giving the drug, or I might need to change the drug itself. You got it? This is the concept that we'll be talking about. طيب, let me go back to the normal situation. Okay, I have KEL consisting of window of Km and Ke. So if there is the dose inside, يعني in the compartment I injected my dose. Let me write it here. Dose. No, it's not writing. Dose. Okay, I injected the dose. It will go طبعا eventually في النهاية it will go through this window. But how much will go here and how much will go here? It depends on the size. Okay, so if I say Km, هذا الKm, the size of this Km divided by KL اللي هو total size. وكمان I said Ke divided by the total size اللي هو KE. Okay, this fraction هذا راح يعطيني fraction, يعني لأنه KM will be either equal or smaller most probably than KL, وهنا smaller. نفس الشيء هذا smaller. So it gives me fraction. This fraction we call it fraction metabolized. يعني قديش نسبة الميتابوليزم من الدوز. It's giving me by the size of the km compared to the total size. لأنه الدوز will go through both windows depending on their sizes. فthe fraction of the dose metabolized will depend on the size of the window اللي هو km compared to the total size. نفس الشيء, the fraction that is excreted depends on the window for excretion divided by the whole window. Okay, so this gives me Fm and this gives me Fe. Now Fe plus Fm should give me 100%, يعني واحد, fraction 1. You got it? So if I have a dose when I injected this dose, eventually it will leave as metabolized and excreted. كيف؟ FM اللي هو fraction excreted multiplied بالدوز, قديش صار له excretion multiplied في الدوز, زائد fraction excreted multiplied في الدوز. I can write it also as M infinity. M infinity إذا شو تمثل؟ اللي هي the fraction of the drug that will be metabolized plus the fraction of the drug that will be excreted in the urine. Okay? واضح؟ I can also write Fm اللي هو fraction excreted. I want you to understand this, okay, because there are different ways to express them. Fraction metabolized can also be equal to M infinity divided by a dose. And fraction excreted can be also U infinity اللي هو total, هدول يعني infinity يعني total excreted, هيك مقصود فيها. Because you remember that the drug will be eliminated after very, very long time. That's why we call it infinity. So F excreted is equal to U infinity divided by dose. Don't forget the dose. شو هو الدوز؟ الدوز is equal to M infinity plus U infinity, because eventually the dose that I inject will be removed from the body. Okay? إذن what we talked about is different ways to express what happens to the dose that I inject. It can be metabolized and it can be excreted depending on the sizes. Okay, and we learned that if most of the drug gets excreted and the fraction excreted اللي هو KE على KL is closer to 1, يعني معظم most of the window is KE and it got blocked, يعني there is kidney failure لأنه through the kidney we have excretion. In this case we will have إيش؟ We will have toxic concentrations if we keep giving the drug by the same dose and frequency. بس شوفوا, if I have problem with liver, it might not affect overall elimination of the drug because the liver only has minor role to play in the elimination of the drug. Okay, so let's talk a little bit about the kidneys and focus on excretion. How can we assess the kidney function? يعني how can I say the kidneys are working okay, bad, good? How can I do that? We can do that by measuring the filtration or the removal of creatinine from the body. Now, creatinine comes from creatine phosphate, and creatine phosphate is available in the muscles. The metabolism of creatine phosphate is done in order to get energy. This releases creatinine. Okay, يعني من creatine phosphate gets metabolized to get energy, and this will leave creatinine. Creatinine will be in the bloodstream, and from bloodstream it goes through the kidney, and it's mainly filtered. يعني في الكدني what happens? It's mainly filtered في الكدني. طيب, if we look at the kidney can remove the drug by different ways. For example, we have the mechanism of one, glomerular filtration. يعني الفلتريشن بيصير بال اللي هو البومان's capsule filtration. Also it can remove the drug by secretion, or usually active secretion. Also we have a process that is reversal, which is reabsorption. إذا خلونا let's look at the Bowman's capsule here. We will have filtration here, and then here we have active secretion and reabsorption اللي هو بالdescending limb أو proximal tubule with distal tubules. So we have different processes affecting the removal of the drug في collecting tubules, وبعدين في النهاية it gets removed from the kidneys. Okay? Now for the filtration, Bowman's filtration, glomerular filtration rate, the normal glomerular filtration rate is 120 to 130. This is the normal filtration rate. 120 to 130 ml per minute. انتبهوا على اليونت. الفلتريشن كأنه بفلتر من البلازما that comes. It filters من هذا البلازما comes to the kidney at about 650 ml per minute تقريبا. 650 ml per minute. This is the plasma, not the blood. Blood is almost double. طيب, من 650 قديش منهم بتفلتر؟ How much gets filtered? 120 to 130 ml per minute. Now this creatinine is, and we will talk about creatinine probably later, but this creatinine almost completely get removed from the body through filtration, عن طريق الفلتريشن. إذا creatinine gets removed mainly through glomerular filtration. في هناك شوية about 1 to 3% active secretion, but mainly it gets removed through glomerular filtration. حلو؟ طيب. That's why we can use creatinine to assess filtration. يعني if I know what is the filtration rate for creatinine, and in this case we will call it clearance of creatinine. Clearance إذن هو عبارة عن, it's like filtration rate. If I know the clearance of creatinine, شو filtration rate of creatinine, then I can assess the filtration rate اللي هو glomerular filtration rate. أعيد. Creatinine is removed from the body mainly through the kidneys. في الكدني, what is the process by which creatinine gets removed? Mainly, not only, but mainly by filtration. طب شو الفلتريشن للنورمال كدني؟ It's 120 to 130 ml per minute. If I know what is the clearance or filtration rate of creatinine, I will be able to say whether the glomerular filtration is good or not. يعني for example, if I find that the creatinine clearance is 12 ml per minute or 12 to 13, شو معناته? And it's supposed to be 120 to 130. معناته here the kidney is working by 1/10. شوفوا 10. 1/10 its normal ability. طيب, I already talked to you that glomerular filtration is only one mechanism by which drug is removed. There are other mechanisms. Well, according to one theory, they say if, for example, the glomerular filtration rate is affected by 10 or 20 or 30%, the whole kidney function will also affected by the same percentage. That's why if I am able to measure the glomerular filtration rate of the kidneys or estimate the glomerular filtration rate of the kidney. أنا حكيت لكم measure و estimate لأنهم they are different. Measure means يعني determine exactly. Estimate يعني approximately. The creatinine can give me approximate glomerular filtration rate. If I am able to do that, okay, I will be able to know how the kidney function. And if I know how the kidney function, I will know the effect. مش هاي اللي حكينا عليها الكدني KE. I will know the effect on the KE. And if I know the effect على الKE, I will know the effect على الKL. And I will know what will happen to the elimination of the drug. Okay? طيب. If I measure creatinine clearance and I estimated the GFR to be from 60 to 89. طبعا this is less than 120 to 130. In this case, I can describe the kidney as having mild decrease in kidney function, mild, خفيف. If the creatinine, if the GFR is 30 to 59, بيكون عندي moderate. Moderate يعني معتدل, أكثر من mild. Okay, mild خفيف. هذا زي كأنه we are talking about middle, average. Moderate decrease in kidney function. If it is 15 to 25 to 29, sorry, then I have to say that there is a severe decrease in kidney function. If it is less than 15 ml per minute, then I have kidney failure, and in this case I need dialysis. سواء اللي هو sorry peritoneal dialysis مثلا, okay, أو blood dialysis. Anyway, I need to do dialysis. Okay, this is kidney failure if it is less than 15. Okay. Now in each kidney في هناك about 1 million nephron, والنفرون هو ال functional unit أو ال basic unit responsible for the purification and filtration of the blood. We already talked about how the nephron look like. This is the kidney, and the kidney is used. The kidneys are used mainly to excrete the drug and metabolites as well. I want you to know that almost all drugs get filtered. كل الدراجز تقريبا معظم molecules except large ones زي الالبومين مثلا اللي في البلازما, they don't get out, they don't get filtered because they are big. Otherwise almost everything يعني, for example, minerals, salts, glucose, everything gets filtered. What happened next is important, because for example, if glucose gets filtered and it doesn't come back, ايش بصير اليورين؟ اليورين will be sugary, sweet, and we will lose energy very quickly. That's why for normal person, all glucose that leaves through filtration gets absorbed by active process. They get back. وبيجي معهم الصوديوم as well. طيب. Now, let's suppose the following. What we want to do now is to show you the effect of kidney failure or kidney problem on the elimination of the drug. Here, suppose you measure the creatinine clearance. The creatinine clearance gives you ايش حكينا؟ gives you estimation of GFR. طيب والGFR شو حكينا؟ gives you a description of how your kidney is working. Okay? طيب, let's suppose that the creatinine clearance is 10% the normal. 10% يعني بدها تكون from 12 to 13 ml per minute. Okay? Let's suppose that. So, because it's 10%, this means that the window for excretion, هذا الويندو شو راح يتحول؟ راح يتحول ل 10%، يعني only a small portion of this big window, small portion will be used for excretion. That's what does it mean. So let's go back to the example. We measured creatinine clearance. It's 10% of the expected, the normal one. And for a drug vancomycin, the fraction excreted is قديش حكى؟ 0.95 0.95. طب شو معناته بده يكون الفراكشن ميتابولايزد؟ مش حكانا fraction metabolized زائد fraction excreted 1 معناته this will be equal to 0.05. اوكي. طب وشو الفراكشن excreted؟ هو عبارة عن KE على KEL, right? طيب شوفوا شو is given. طيب معطينا الدوز، معطينا الفوليوم distribution، معطينا السي بي 0. وهنا المهم it's giving us the normal KEL. شو النورمال KEL؟ 0.116 يعني 6 hours. الهاف لايف تاعه 0.116 hour to the power of minus 1 يعني الهاف لايف is 6 hours. كيف عرفت 6 hours؟ خدوا 0.693 divided by 0.116. طب شو بده؟ What I need you now to do is tell me for this patient who have a big problem في his kidney because it's only 10% عنده kidney failure. What will happen to the half-life of the drug? What do you expect to happen? In this patient who has kidney failure, the half-life will increase a lot. كيف عرفت طيب أنا a lot? Because most of the drug is going through excretion and excretion is having a big problem. That's why I expect that the half-life will increase a lot. طب how do I work with it? Okay, شوفوا شو بحكي لكم. Most of the drug gets by excretion. fraction excreted is equal to KE على KL. إذا في الحالة العادية I will write that 0.95, this is a normal case, is equal to اللي هو ال KE, which I don't know, I didn't calculate KE yet, divided by KL, which I know. KL قديش؟ 0.116. So divided by 0.116. طيب, by doing this, I can actually calculate the KE as equal to 0.116 multiplied into 0.95, and KE is giving me as 0.1102. طيب شو اليونت؟ زي ال KL, اليونت is hour to the power of minus 1. طبعا now I'm talking about normal patient. I'm not talking about someone who's having kidney problem. طيب عرفت ال K, can I know KM؟ شو ال KM؟ للنورمال يا إما بدها تكون either it's KL minus KE. ليش؟ لأنه ال KL هي عبارة عن it's KM plus KL. Either it is this one, or I can do it by looking at FM واحكي انه ال FM is equal to 0.05 which is equal to Km divided by KL. So I can use any of these two ways. طيب, in this case, let's suppose I want to use this one. عندي ال KEL اللي هي 0.116 يساوي, بس I need to remove the negative, اللي هو 0.0058. إذا ال KM 0.0058 joule unit, also hour to the power of -1. طيب, that is expected انه يكون عندي ال window of metabolism very small, لانه شوفوا 5%, very small compared to the KE which is اللي هو ال excretion rate constant. Okay? طيب, so far so good. Now what I did is everything regarding a normal patient. طيب, now for this patient that I want to treat with vancomycin, في عنا problem في ال window of excretion ال KE اللي هي kidneys, انه ال kidney is working by 10% of its ability. إذا شو بده يصير في ال window هون؟ It will be 10% of this number, of this size. طيب, فإذا شو بحكي؟ بحكي KE of the patient تاع ال patient هلا is equal to النورمال اللي هو ال 0.1102 multiplied 10%. 10% يعني 10 by 100 يعني or 0.1. So if you do this, you will get the following number 0.01102 joule unit hour to the power of -1. طيب, إذا هلا أنا طلعت ال KE تاع ال patient. طب شو ال KM تاع ال patient؟ ال KM تاع ال patient is not affected, it is the same because he has no liver problem, he only have kidney problem. فإذا لهذا ال patient, this is the new KE, okay, and his KM is already given as 0.0058 and his K is 0.01102. So if I add them together, what will I get? So this is 0.0058 اللي هو ال KM plus 0.01102. وشو بعطيني هذا؟ It's giving me the KEL of the patient. يعني this number هو ال KL تاع ال patient, what you see here 0.01682. طيب, خلينا just remove these things. Okay, so let's write the number we got for the patient. طيب, شو هذا ال 0.01682؟ 0.01682 hour to the power of -1. هذا هو ال KL تاع ال patient. هذا هو ال KL تاع ال patient اللي هو عبارة عن هاي KE عبارة عن ال KE of the patient which is really affected plus ال KM gave us this KL. طيب, شو تأثيره على half life? What is half life equals to? T half equal to 0.693 divided by the KL of the patient اللي هو 0.01682, and this will be equal, let's see what happens to the half-life, 0.01682 divided by, sorry, not this one, 0.693, هذا 0.693 divided, what happened? Okay. 0.693 divided by 0.01682 equals, راح تشوفوا عندنا more than 41 hours. طيب والoriginal قديش؟ 6 hours. Now it is the half-life is 41 hours. شوفوا قسموا 41 hours half-life of the patient هذا ها. Patient. This is for patient. Patient قسموها divided by the normal. يصير عندكم في هناك 7 times النورمال half-life. إذا patient half-life تخيلوا is 7 times the normal half-life. This is a very big problem. If we look at the normal way, this is for a normal patient. شوفوا في increase. Initial dose is initial concentration is 15. صار بعدين 24 maybe. بعدين صار 27 or 26 etc. But for this patient شوف بدأ فعلا 15 بس شوفوا كيف صار. Now it's about 30 and then more than 40, so we will have a big problem. Now compare what we discussed to the following example when you are using erythromycin. Erythromycin, the fraction excreted is 0.15. معناته if I have the window of elimination فقط 0.15 is for Ka. So يعني 15% من الويندو is Ke. 15% لأنه 0.15. الKL التوتال هو 0.58. اوكي 0.58 طبعا hour to the power of -1 معناته الهاف لايف is 1.2. طيب what I want you here to know and then you might try it by yourself is that most of the elimination happens from or through metabolism. The problem that we have is in the excretion in the kidney اللي هي if we assume that 10% or the kidneys are working by 10%, they are their normal function, only 10%. See, if even you remove all of this one, the effect on the total KL will not be very significant. That's why مش رح يأثر, it will not affect the half-life very significantly. So if you do the same steps we done in the previous example, شو رح تحصلوا? You will find that the new half-life for this patient, the new half-life is 1.4 hours, and for normal patient is 1.2. It's even not double. يعني if we say 1.4, how many times it increased? 1.4 divided by 1.2. شوفوا it's 1.17 times the normal half-life, which is not a lot. يعني هذا لا يعتبر a big problem with the drug, and we may continue with the normal dosing of this medication. I hope this is clear for you. If you have any question, you can always ask me. Okay. Now we will be talking about clearance. Okay, I told you previously that clearance is very important term, It's even more important than KEL. First of all, we will start talking about the definition of clearance, and then we will see the importance of clearance in pharmacokinetic. Well, the definition of clearance is the volume, انتبهوا, the volume of plasma which is completely cleared of drug per unit time. The volume of plasma which is completely cleared of drug per unit time. معناته شو اليونت؟ اليونت will be volume per time. So volume per time, this is the unit, and it's similar to the filtration rate which I described previously في الكرياتينين clearance أو بالglomerular filtration rate. We talked about a similar thing. Now, with equation, we can define clearance as the rate of drug elimination divided by concentration. Rate of drug elimination, أو خلينا نحكي the amount of drug eliminated per unit time divided by the drug concentration at midpoint time. But first, let me talk about the concept. Let's suppose that you have this compartment, okay? وهون you have the window for elimination اللي حكينا عليها KL, okay? And in this compartment, okay, let's say you have 100 liters. الفوليوم هذا is 100 liters. And in this 100 liters, let's say you have 100 milligram. معناته شو الكونسنتريشن؟ concentration is 1 milligram per liter. Okay? طيب. Let's say this is at time 0. Now, after 1 hour, طبعا, some of drugs left. Let's say that هذا طبعا after 1 hour. انتبهوا. 1 hour. After 1 hour, you found that the amount of the drug that is left is equal to 10 milligram. Okay, 10 milligram. طيب. معناته how much of the volume اللي موجود هون, how much is completely cleared? إذا الواحد مليجرام is in 1 liter هنا مليجرام. طيب اللي بعد 1 hour قديش؟ 10 مليجرام. طب 10 مليجرام راح يكون في كام لتر؟ في 10 لتر. اوكي؟ طيب 10 لتر، إذا 10 لتر كأنه 10 لتر من هون من ال 100 liters 10 لتر is completely cleared per unit time. شو التايم اللي صار فيه الكليرنس؟ I told you 1 hour. That's why the اللي هو clearance of this drug is written as 10 liter اللي هو completely cleared of drug per time اللي هو in this case hour, so I put it as hour. Okay, so you can see that it's easy to visualize what is happening to in terms of clearance when we say 10 liters per hour. معناته every hour 10 liter gets completely cleared. Okay, now is clearance constant? Yes, it is constant. And if you remember, I defined it as an equation as rate of elimination. Let's assume that it is delta U, how much drug eliminated per time, and that is divided by concentration. For how much gets out during a time divided by concentration. Someone will tell me, well, the amount that is getting out is decreasing with time. صح? Because it's decreasing with time, so clearance should not be constant. Not constant. That is wrong. It is constant. Because yes, the rate of elimination is decreasing, but also the concentration is decreasing. إذا في عنا decrease في both sides. في concentration الموجود هون will decrease. وكمان بالrate of elimination will decrease. So it will keep the clearance constant. The clearance, as I said previously, is even more important than KEL. طيب, this is how we can write it. We can write it as du على dt أو amount, rate of amount eliminated divided by concentration. هنا concentration انتبهوا it's at midpoint time. يعني لو بدينا من time 0 ل 1 hour, this CP is at half an hour. Okay. طيب, another thing, if we go back to this figure here, let me draw it again, sorry. You have this compartment, you have this compartment, okay, and from this compartment the drug gets removed. هنا في عنا ايش؟ DCP على DT, and we agreed, اتفقنا انه this is a negative value. Why? Why is it negative? It's negative because the concentration is decreasing here. If you are at this side, the opposite is happening. شو يعني the opposite is happening? It's decreasing here but increasing here. Because with time more drug gets out. It's accumulating outside. We said this one is equal to minus KL في V. So this one is the same. Sorry, KL في CP here. Okay. This one is the same. So it's KL في CP, but it is ايش؟ positive. Also كمان here we are concerned with amount, not concentration. الامount اللي بيطلع من الدرug, not concentration of drug that gets out. Because we are concerned with the amount, we multiply this by volume. Then when you multiply concentration by volume, you get the amount of the drug that is getting out. فشو بصير الديو؟ على DT it will be equal to KEL في ال V في CP. واضح؟ إذن we multiplied V في CP to get the amount of the drug that gets out from the window, whether metabolism, excretion, or both. So it's equal to KL في V في CP. طيب, why did I do this? I did this because I wanted to use this equation. شايفين du على dt اللي KEL في V في CP divided by CP. بتروح CP مع CP شو بضل؟ KEL في V. إذا شو ال clearance of a drug? It's equal to KEL multiplied في V. طيب, if I'm only concerned with, شوفوا هاي the same one, but I want to use KE, يعني مش الشباك كامل, not the whole window اللي هو consisting of مثلا KE, KF. لا, not the whole window. I just want this one. In this case بصير عندنا renal clearance بنحكي له, and it will be equal to ايش؟ KE في V. Okay. طيب, if I want اللي هو الميتابوليزم, clearance by metabolism, بصير KM في V. طيب, if I want to add them together, اللي هو clearance, renal clearance and clearance by metabolism, I will get the total clearance اللي هو KL في V. بتصير عندنا ايش؟ renal clearance زائد clearance, sorry, let me remove this one, clearance plus clearance by metabolism will equal to, شوفوا V مشترك بين الاثنين multiplied في KM plus KE. طب وال KM plus KE شو هم بعطونا؟ the whole window اللي هو KEL. اوكي؟ بصير V في KL او KL في V. هلا I told you previously that clearance is even more important than KL. One of the reason for this اللي هي اليونتس are easier to imagine and visualize. شوفوا لما حكيت لكم 10 liter get cleared, completely cleared of drug. You can imagine it that in 1 hour 10 liter out of 100 liters get completely cleared of drug. Okay? The other thing, it can be related to the efficiency of the organ of elimination. Efficiency of the organs of elimination. كيف يعني? For example, if I tell you that the plasma flow rate to the kidneys are equal to 650 ml per minute. Okay? إذا the flow rate to the kidney 650 ml per minute. If the drug is 100% efficiently cleared by the kidney, لازم يكون الكليرنس وقتها ايش؟ clearance of the drug also equal to the plasma flow rate اللي هو 650. شو معناته؟ What does it mean? Okay, it means that anything that reach the kidney, any of the drug that reach the kidney gets removed directly. خلاص بطلع ما في بيرجع للبلد. Nothing comes back to the blood. طيب if there is another drug with a clearance of 1 ml renal clearance 1 ml per minute, هل بعتبر انه do I consider that the kidneys are efficient in removing this drug? No, they are not efficient. انتبهوا, please pay attention. 1 ml per minute does not mean that the kidneys are not working well. It depends on the drug and the patient. How do I know if the kidneys are working well or not? That is, as I already discussed it before, through creatinine clearance. عن طريق الكرياتينين clearance. It should be 120 to 130 ml per minute. أما for a drug to have 1 ml per minute, that depends on not only the kidney function. Kidney function can be excellent, but it depends on the property of the drug as well. Okay? طيب, إذن it can relate to the efficiency of organ of elimination. So if we compare how much plasma or how much blood goes to the organ of elimination, liver or kidney, and how much is removed, I know that whether this organ is efficient in eliminating the drug or not. طيب, also I can investigate the renal or hepatic function by measuring the elimination of certain drugs or certain materials or certain endogenous material. كيف الكرياتينين؟ We use the creatinine which is endogenously produced. We used it لإيش؟ To know how the kidney function. We have similar thing في liver which we can use to measure the liver function. Okay? That's why for all these reasons clearance is more important than elimination rate constant. Also, I want you to know that clearance is directly used when I want to do dosage regimen. نستخدم الكليرنس. KL alone is not enough. Okay? طيب إذا renal clearance is equal to Ke في V, clearance by metabolism is equal to Km في V, total clearance is equal to renal clearance plus clearance by metabolism. Also, another way to calculate clearance is اللي هي renal clearance, as you see it here. This is another way. Renal clearance is equal to how much drug gets eliminated في urine or by excretion divided by the area under curve. هاي الarea under curve we already talked about it before. And clearance by metabolism can be calculated by amount of the drug that is going to be metabolized by also AUC. If you add them together شو بصير عنا؟ بصير عنا total clearance is equal to U infinity plus M infinity, يعني الدوز divided by AUC. إذا بتتذكروا ال AUC كيف كنا كاتبينها؟ AUC is equal to dose divided by V في KEL إذا بتتذكروها. If you remember it. Now this is clearance, if you remember. Now the good thing, you remember when we talked about trapezoidal rule, and we said this rule, the approximate numerical estimation of AUC, is very frequently used because we do not need to assume the number of compartment. Okay? فإذا if I calculate AUC and I know how much dose I am giving, I can calculate the clearance. Because if I use trapezoidal rule, I do not need to assume a certain model, يعني a certain one compartment or two compartments, etc. I do not need to do that with trapezoidal method for the calculation of AUC. We call it model independent method. Model independent method. يعني I do not need to describe this as one compartment or whatever. Okay. طيب, look at the equation here, which I already discussed before. طبعا the clearance here is, طبعا I'm assuming this is the amount of eliminated, whether through urine or through metabolism, both. Okay. How much eliminated per time is equal to KEL في V اللي هو clearance multiplied CP. إذن if I want to have a graph, in this graph I put CP here, okay, the concentration here, and how much gets eliminated here, the y-axis. So this is y and this is x. You will see that at zero concentration nothing gets out, 0 0, and as you increase the concentration, more of the drug is getting out, is getting eliminated. The slope of this one, of this line, the slope will be equal to to the clearance. Okay, so this is another relationship that you need to be familiar with. طيب, again, I already talked about this. This concentration is at what time? شوف عندنا هنا time, 2 times. في عندنا, let's say at 5 hours, this is one time, وفي عندنا at, this is an example طبعا, let's say at 6 hours, في عندنا, and we have also at, let me write it again. So we have at 6 hours and we have at 5 hours. Let's say this is your delta T. So it's 6 minus 5. Now this concentration is at what time? Is it at 6 or at 5? Don't forget, this is at midpoint time, يعني at 5.5 hour. Okay? إذن بين الساعة 6 وبين الساعة 5. Between hour 5 and hour 6. I hope this is clear. I hope you enjoyed the video, And if you have any question, as usual, you are most welcome to ask me.